It's always good to come after lunch. Everybody is feeling fully energetic. Yeah. So my name is Patrick Schittekat. My last name is maybe a bit difficult to pronounce, so just call me Patrick in the hallway. I will be talking about out-of-order execution. What can you do for me? Out-of-order execution is the paradigm, the prevailing way that hardware CPUs nowadays try to get performance out of your code. I will be talking about the advantages of that, and I will be talking about the limitations of that. Basically, this talk is a call-out to start understanding hardware CPU better, such that we can tune our code better. So this will be a bit of a bottom-up talk, a bit different than a typical C++ talk that we have seen here, but I try to entertain you, especially when it's after lunch. So great. So why this is a call-out? Why is this a call-out? Why is hardware CPU knowledge about hardware CPU increasingly more important? For that, I will take you back to 1959. See this big computer, etc. And Feynman said, there's plenty of room at the bottom. He didn't mean there is plenty of room on the floor to put more of these bigger things. No, it was plenty of room at the bottom. At the bottom meaning between the software and the hardware stack. Hardware was lots of room to miniaturize at that time in 59. On top of that, afterwards, Dennard scaling maybe in English said, if we could make the transistors smaller by a factor of k, we could get the power density, keep the power density constant, and increase the frequency with k, which was a free lunch basically. Yeah, we could make faster CPUs, smaller CPUs, and they don't dissipate heat so much, or that was keeping constant. So that went well for a while, until around 2005, 2007, where we couldn't shrink we were shrinking the transistors, but with that we also needed to shrink the voltage, and that was not possible anymore to put it lower under a certain threshold. If we went below that threshold, then current starts to leak, transistor starts to leak, and power starts to dissipate. Yeah. Also, we were pushing a bit the frequency faster than this law of Dennard scaling, so we got there a bit faster than we anticipated. As a consequence, you see here, we couldn't increase the clock frequency anymore. We actually lowered it and decided to have multiple cores. Multiple cores here. And you see single core performance. So each point in this graph, which is the x-axis per year, and the relative performance on a well-known benchmark spec-int, you see that it's declining, and well, this is a bit similar. Yeah? It's declining, especially single thread performance. And here, if you have multiple cores, then it gets better. But that means that we needed to change our programming model. We need to think about threads, and not every program is made to make thread level parallelism. Okay. So that's why performance tuning gets much more important. We can't improve the performance of our hardware so fast as we have did before, but so we need to work on the input to that computer, to this chip. So we can do that in different ways. We can take our existing software and try to remove some of the bloat, tailoring the software to specific hardware features, and that's what I'm going to try to do, talk about this today. Or we can make new algorithms, or we can possibly rethink this out-of-order execution model. How can we make it more simplified? How we can make it maybe much more to the point for a certain workload. So that's what's meant. With this slide, there's room at the top, maybe not so more at the bottom, even though Intel and AMD will tell there's still room at the bottom, and to a certain extent I agree, but it gets difficult. But we have room at the top still, if we just know also much better this hardware execution model. Okay, so let's start. So we expect now, what you can expect further in this talk is that I'll give you insights how a modern CPU core works. We'll try to tease out some CPU features using macro benchmarks, some well-known, some lesser well-known, and analyze some C++ workloads on modern CPUs in a top-down way. Because this talk will be top-down. It will start from not the nitty-gritty details, but it starts from the top of a basic knowledge of the out-of-order execution model. Okay, an almost arbitrary C example. I say almost because I needed to find a simple enough example such that I can get it on my slides. If you want, you can compile this and you do an object dump, and then you will get also the instructions, x86 64 instructions on here on the right side with some more information, etc. So let's go over this example. So here, parameter A is ADX. So you have a function that takes 3 inputs and tries to set the result into the output memory out. You have B, which is ECX. Then we have a pointer, X, pointer Y, to some area, to some memory allocated stuff. This is the pointer to the output result. And what we do with it, we add whatever is in X with A. And we multiply whatever is in Y with B. And then we subtract the result. And we store the result in the output register. Now, this is on the right side to see what's in binary, of course, in memory. This needs to be fetched by hardware, by the CPU. And this needs to be decoded. This needs to be decoded into instructions or to something that the machine understands and to kind of configure the whole hardware to do its thing. These instructions on the right side are not used directly. They're disassembled even to smaller or decoded even into smaller macro ops, as you can see here. For example, the add, we normally take EDX and the pointer and then put the result back into EDX, but instead the macro ops are split for this add. First you have a move that gets the memory. It gets, in this case, X from memory and puts it in register 1. And you also have the add then with the register 1 that you just have filled with the value. And the same for multiply. Now, this is a bit made-up macro-op language. We don't know how Intel exactly encodes this in the Intel or others. Encode this internally. But what we do know is that they have more than the 16 registers that you can use from the ISA. They have around 200, etc. So they add, so you can add physical registers, and you also would do that to avoid false dependencies because you only had 16 registers, and if you could split them up, then something doesn't depend on something else. Okay? So how would a CPU execute these micro-ops in order? So to explain out of order, I will try to first say what was the in-order concept, what was our method execution model. So we load this one, and then we have a cache miss, for example, in a CPU. It was the first time we did it. It was a cache miss, 20 cycles, maybe more. 1,000, 100, million, depending on how far we need to look in the far memory. So what happens with in order? This add can't be executed, and it stalls. It stops. It can't go any further because R1 is not ready yet. Okay, do we get a better performance when it's out of order execution? So this is a small example, but you should see that this happens like on a big scale in a Intel or AMD CPU or any core that uses out of order execution. So here we do the load again. We have the cache miss, 20 cycles. We have the add. But we are out of order, so we continue, and later on we come back when the register 1 is ready. We load Y into R2, and we can do already the multiply. So that's the reason why out of order gets a better performance than in order, if everything else is the same. So because out of order execution can overlap long latency micro-ops. If you have, for example, three loads that you need to do, and they all hit L2 cache or even L3 cache or even memory, they can be done in parallel. In order, can't do that. So they won't pull instructions up and execute them as fast as they can when the data is available. So in summary, out of order execution, they analyze your dependencies between your instructions and will check whether values are available, operands are available to be able to execute things already when it's there. And not wait and not stall. Yeah? Okay. So this is a modern out-of-order CPU, very modern. So you have the front end who did this fetching and decoding and gives the micro-ops to the backend who does actually the actual execution, where you have more, you have different functional units for multiply, LU, and load operations, all specified in many documents of Intel and AMD. But they want to try to do even better, so they add branch speculation. So what does that mean? So branch or control speculation. So let's suppose that every dot is what we call a basic block. This is a block of code, instructions, like you have seen before, and it ends with a jump instruction telling if it's true, this comparison somehow, then you go to the left side, or otherwise you go to the right side. Left side means branch taken, so you need to jump into the memory to get your new basic block to the first instruction of that. Or branch not taken means, so the red one. Okay, think about green and red a bit differently now. So right, let's just say left or right. Yeah, right is a branch not taken. So that means that you can just follow through and keep on fetching. You don't need to jump and incur extra cycles to go and fetching. Now we come to the colors. You have the green ones, you have the red ones. So let's suppose you're following, you start on the top, and you say, I fetched this and I jump, but I don't know yet what the outcome of my comparison is. The backend didn't tell me yet. What was the result of this? What do? Do I stall? Then we need to wait. Why can't I just fetch more? What do I need to do then? Okay, I predict that I will go for the left side. That I will need to take this jump. So we go for the red one, the green one, for example. So every time we predict, so in every node we need to make a decision. Sometimes that will be a good decision. Sometimes you will be on the wrong path. So in this case, the happy path or the correct path was all the way down up to here. If you would have predicted at the right decision at the right time, then we would end up here and no problem. We started even executing instructions that at the time that we were executing didn't know that we should have done it or doing it. So, but let's suppose you ended up on the right side. You discover a wrong prediction, that you're here, so you have predicted all this wrongly, so you're on a red path. Then you need to basically reset your hardware and go back. somehow to the last known well decision to keep program semantics, and especially in the case of exceptions. What if you throw an exception in the wrong path? Should you give it to the user? Should you give it to the client? That won't be nice, yeah? That you get exceptions of executions that actually didn't need to be executed. And in fact, this in the early days of out-of-order execution, they tried this model. It was fast told, no, this is not good. Yeah. So in order to accomplish that, we can actually send exceptions back or know what the right path was, or go back to the right path. They introduced something like what's called a reorder buffer. So a reorder buffer is filled from the front end. Here, whenever, always press the wrong button. So whenever something is decoded, it also goes to the reorder buffer. You have a micro-op 1, micro-op 2, micro-op 3. This is the sequence how they are in the reorder buffer. They can have different data structures, but they know the order in which they have come. And now, you have seen 2 green ones. These mean that they are retired. These were executed at the end, committed, retired. They were at the right path. So if you have an exception, for example, in micro-op 4, it will wait to retire until you have done micro-op 3 and that it's known to be on the good path. If not, you would, so let's suppose you had this exception, you would go back and flush and set all these things on invalid, etc., and start back over on this 2 green ones. And so that's how we deal with speculation, etc. Okay. That's somehow clear? Yeah? So this is something you can read from the Intel architecture, but what is the size of the reorder buffer? This is an important question because how big the reorder buffer is, how larger it is, the more instructions we can do out of order, the more performance that we can get. And of course, that comes at a cost, at power usage, etc., energy usage, so you can't do everything, but it's an interesting thing to know what is the reorder buffer, especially when you don't know exactly the machine. So how would we try to tease out this? How would we know that the reorder? We can use some assembly. And therefore, before I show you the example, you should know that there is an instruction that's called a micro-op, that's called no-op. Or in short, NOP. Yeah? So no-op. And a no-op doesn't go to the backend. A no-op goes only to the reorder buffer. So what we can do is, let's suppose we start with a load, then we have 1 no-op. And we can check the time, how long that takes to be executed. And we can do that for a load, no-op 1, no-op 2, and we can check how long that can be executed, and so forth. So in the end, we could have a series of loads with no-ops and a load behind, and see when that falls off into the reorder buffer, when it can't be filling the reorder buffer anymore. Because if you have an instruction and the reorder buffer is full, then the machine will stall, the front end will stall, and you won't be executing this load anymore until there's place available in this reorder buffer. So if the reorder buffer is full, you have a load, and you have, let's suppose the reorder buffer is 20, and you have 19 no-ops, then this second load, will not be in the reorder buffer. So it needs to wait until the other load is done. So then we will get a spike in our CPU time. So if you see that, so this is the total CPU time on the y-axis. On the x-axis is basically the number of no-ops that you have put in between every time, plus 1. So here we have 16 no-ops or 15 no-ops, 49 no-ops, 84, and so we go on. So here you see gradually increasing because it requires a little bit more effort to keep this reorder buffer. But here it jumps around 512, which I know was the correct one because I looked it up. It was a Raptor Cove and it has 512 reorder buffer entries. Because you see here that the time to do the 2 loads spikes, that means that they were not executed out of order. They were serialized because one needed to wait until the reorder buffer was free with the load that was done. So we have detected our ROB size, ROB, reorder buffer size. So in that you can do also to do other type of CPU features to get out. We will see another example in a minute. Is that okay? Yeah? Okay, another type of speculation is something that's less known. Also, it's not so commercialized by in the optimization manuals, etc. But it's good to know. There's also some speculation going on in the backend, and it's called memory disambiguation. So I will tell you with this drawing what that is. So let's suppose in the program order you get the store. So in your instruction fetching, you get a store to a certain memory location before a load. So the store before the load. Out of order, what would it like to do? It would like, if it can, if the load, if the address is available, it will already start loading and actually doing it before it's known. The store, the address of the store is known, or before the store. Is this allowed? Can we do this? Huh? Almost name, address. So it has this is allowed if there's not overlapping addresses for the load in the store, because otherwise you will be already have loaded. Which happens to be a stale value because the store would have given you the new value. So if it's not overlapping addresses, you're all fine. Except when it's overlapping addresses, then you're not allowed to do it. So doing this, that's called load hosting. Actually, this too, but that's wrong. Yeah, so load hosting is doing it before the store. Now, CPUs are very good at it. Especially this is again easy decision. It always takes transistors, etc. But if you know the address of the store and if you know the address of the load, then you can basically compare it and discuss and basically decide should I do it or not, load hosting or not. But what happens in most modern CPUs, and when they actually introduced it, it gave a 10% improvement in the instructions per cycle that you can execute, more or less. They actually start predicting it. They start predicting, can I do the load before the store? Before you have the address, before the store is known. The store address is known. And afterwards, so then I have 2 cases. One, in the end, it was okay, so then you don't need to do anything. But if the load and the store address were overlapping, then what you need to do, then you need to clear the whole machine. So again, the whole reorder buffer needs to be cleaned out, the whole pipeline, maybe start fetching again, etc. So that's an expensive operation, about 30, 40 cycles. More than the bad speculation that we have seen before. So, and since this is not so well known, it's also not so much written how it actually works, we can make a small program to start seeing how this is done and try to reverse engineer this. So all in the spirit of getting to know what the hardware, what the CPU is doing. So you see here, this store load function is actually written in assembly. Was quite big, but basically what it does, it basically does a store before a load. It takes 2 memory locations, one for the store and one for the load, as you can see here. Here, yeah, 2 memory locations, yeah. So in this case, memory, 1 basically, or 1000. Here, so store, load. What also is done in this store load assembly language is that you make sure the store address is very late known, with a couple of multiplications of the address multiplied with 1, but at least all these things needs to be done. So you would in this case not know the address before. That is guaranteed by the store load, or not guaranteed, at least some experiments. So what do we do then? We go over. First, we try to kind of reset this memory disambiguation system. So we make it, we always store loading to the same address, so overlapping. So it will reset the counter, it will count down, and then at the moment say, I'm really not going to do it anymore, because we get all these machine breaks. And then the fun starts. So now we make hoisting back possible. So from iteration 200 to 2020, we say, do the store and the load, and it has non-overlapping memory addresses. So it will tell, at some point, I can do load hosting, I can do this load before the store, no problem. And then here, we're going to be a bit nasty. And all of a sudden, at iteration 2020, we do a store load on the same address. So what will happen? What we will see? Yeah, so you will see somewhere before it stalls, what you will see. Yeah, you will see a dip, right? Because you have here at some point it will think, hey, this is here I can do load hosting. So you will see that it takes less CPU time. So maybe I needed to take averages, etc., a bit more, but I tested this basically the week before I came to this conference. I didn't have so much time, but here we start from the loop iteration 200 to 230. Remember the I, and here this is the number of cycles it took. So here in the beginning, I can go back to this slide. So here we are, and we say, here we have non-overlapping addresses. So from 200 to 220. And so from 200 to 220, we have non-overlapping addresses. But you see, at 215, exactly then, we start to see a drop in the CPU time. This is when load hosting starts. This is when they said, the predictor said, I can really now start doing load hosting and put this load before. And this is also what's in the patent of Intel, around 15 cycles, 50 load store combinations, then we can start to load hosting again. And then it goes well until iteration 2020. Remember, at iteration 2020, we all of a sudden say, do a store load with the same memory address. So what do we get? A big spike. So here we have load hosting. This is how we get a lot of, a lot more performance, because loads are very important to do as early as possible, because memory is getting slower compared to how fast we can get CPUs. And here is what we got, a machine clear. And it takes even longer time than normally serializing, because we need to reset the system and start from the last well-known retired instruction again. So this happens all for you in the CPU. This is quite a lot. I think that's a big advantage. Besides that, this is improving it. You need much more power, and it's power hungry, but this is what it does for you. So, and basically you can, some people of the University of Amsterdam, I think, from the Netherlands. They have reverse engineered how this memory disambiguation works. They also find out, for example, that there is like a watchdog principle. If 4 times you got trapped in machine clear, then they would never try it again until a very long time. Yeah. So there is a. Yeah, you don't need to know the ins and outs of this article, but they basically could sketch this and see how this works in Intel. They did it actually. It was a very nice paper. It's called Rage Against the Machine Clear. So it's actually exposed also a vulnerability because you could get somehow, like in Spectre, etc., some passwords here. So that's why I was. They know this from Skylake, so that's why it was interesting to see whether it's still in the new Intels, which it does when I did the test, as you could see here. Yeah. Okay. Now I think I've talked about the advantages. So what this does for you. So I would like to talk now about limitations. Limitations of this out-of-order execution system, because in a way it's a fixed system in hardware, so sometimes we need to help it shape the input so that it's get helped. So one way of looking at it is top-down. That's why I mentioned this in the beginning. So we have back a very modern machine. Now, if you see graphs of Intel and AMD, there will be much more boxes, etc. But I think this will always be the main scheme, the grand scheme. So I think if you know this, it's much easier to interpret all these boxes and how they are connected when you read the manuals of Intel and AMD. So let's start. So what we know that the front end sends micro-ops to the back end to execute out of order. Now, in most modern ones, now you can send 4, let's say 6 to 8 micro-ops per cycle. And you want to use them as best as possible. I only have drawn 4 because of placement reasons and for other reasons that you will see. So you have, let's say these are all slots. So per cycle, you can put an instruction here that can be executed on the backend. So in the best case, you want this all to be instructions that in the end would have been retired, that needed to be executed, that was not badly speculated and so forth. You would just do instructions, all green ones, that would be perfect. Unfortunately, that's not the case. So some instructions are instructions that are executed in the backend, but in the end didn't end up in the, it was not needed for your program. So this is lost execution. On top of that, in this box for bad speculation is also all the cycles that you waste, or all the slots, pipeline slots that you waste because that you need to go back to the previous state that you know was good. So at that time, you can't start executing anymore. You need to flush everything. So that are all slots that you couldn't use for retired operation or for instructions that can be retired. We have something called, this slot is front-end bound, meaning that is also not a retired instruction, but that are, it's actually not an instruction, it's cycles or slots that you didn't use because the front-end was not ready while the back-end could execute it. So the front-end was not able to fetch things from memory and decode it on time for the back-end. And the back-end was free to do it. It was standing there, hey, what are you doing? Okay, that we call front-end bound slots. Then we have the back-end bound, which is basically, I guess you can guess it by now. So it means that the front-end wanted to deliver something, but the back-end was busy with something and it couldn't accept it. It was loading, or it was stalling on something. All the ports were used, all the execution units were used, or the reorder buffer was full, etc. So that we mean back-end bound. Of course, you can have some overlap if you have at the same time front-end bound and back-end bound.
then it's counted as backend bound, because these all slots need to sum in the end to 100, 100%, or yeah. So what we want to do is to maximize as much as possible the green slots. You won't have slots that are all green per cycle. You want to fill this with useful work that you know that you actually needed to do, and stall as less as possible. But with this scheme, now you have seen bad speculation, memory disambiguation, speculation, how it works with branch and control. This will all fall under that umbrella. And front end, the fetching and decoding that you have seen now too, and also some backend execution, a very small part with the stalling, etc. Yeah. Yes, and that we can use to analyze our workloads and how they run on our hardware from the top down, looking at that too. Because mostly we don't have these micro benchmarks that you have seen. We have big systems, so it's difficult to reason about. You don't know, you have maybe learned some C++ tricks to know this line can be done faster, but in the end, yeah, these are maybe small things that are, yeah, that disappear in the bigger picture. So from my point of view, it's good to also approach these problems from the top down with this in mind, with this model in mind. This, yeah, it's a model. It's not a real system, but it's a model. Yeah, okay, now I gave it away. I wanted to ask, what would be a program that you would say is front-end bound or could be front-end bound? Yeah, Anders. Yes, yeah. Yeah, I was a bit too fast pressing here. Yeah, so the yeah, so compilers. Why, Anders? Yeah, there's a lot of branching, a lot of jumping, probably lots of smaller code with jumps under it. So that gets yeah, it's difficult. So you would. That's also why you see quite bad speculation and yeah, back-end bound, but mostly front-end bound. So again, you can get these numbers by doing this perf command. I assume everybody knows perf. See nodding, so yeah. So you do this perf command and they have a top-down switch. But watch out, you say here top-down all, but you need to make sure that you fix your running to a certain core. Yeah. And make sure that so that you avoid migration, because modern CPU cores are telling, this is getting too warm here, this execution, I migrated to another core until that gets too warm, etc. And then if you want to get the numbers, the statistics, yeah, if you do the whole machine, all your statistics are then from different cores, and you don't know what program did now actually run where. So. And there is also some Python scripts on top of perf from PMU tools, I think from NDC, who does this in a bit lesser, easier, let's say, with easier syntax and a bit better output. So setting it to the first core is C0 task set, and then you can perform a ninja clang, and then afterwards we clean it and we see that we get this type of output. On the console, now it's a figure, 36%. So what can we do about it? What can we do about it on the front end? I can give you a small sample to see the bigger picture. So let's suppose we have, again, an easy function. It gets int A and B, and it can set C, and it can set D. Now I've written in some comments, hot path, cold path, hot path continuous. What does it mean, hot path? Hot path is a path that's exercised a lot. I think most of the time that will be clear. In a cold path, that's something that you don't exercise a lot, only in exceptional cases. For example, here that could be, this comparison could just to check whether you are in an error case or not, so you don't exercise it this a lot. So hot path, lots of exercise, cold path, exercise. So what happens if you disassemble it? And we get our instructions here again. Now you could see, you have here the comparison between A and B. You have the jump that says if, so branch taken if it's yes, or if it's no, sorry. So branch not taken. Then you set it to 1. So here's the cold path, 4. And at offset A starts the hot path again, D3. So branch taken, you jump from 2 to A. And you start fetching from here. So you see it better in this, maybe in this box. So you are here. And then you want to know, you do this you have done this comparison here. Should I jump into another place in memory to get my, go to my hot code? Or otherwise, branch taken or not taken, you just fall 2 into the cold case. So here's the hot case, here's the cold case. As you can see here also in the memory layout, the cold case, hot case. So what would be more optimized? More optimized is that we put hot code, hot code. You should have cold and cold. Yeah, should have maybe find other names. But you want to have the hot code as much as possible together. You want to separate it from the cold code. Yeah? So how can you do that? You have, for example, a C++ attribute that says where you tell. You also can do it in earlier versions. I think this is C++ 20. You can say unlikely. What does the compiler do then? It does some other trickery. It will double some of the the settings to of D to 3. So it has a bit of duplication. But what it do then, it will put the hot code close to the jump. So if you're fetching, you're already there into memory. You just also think about that these other parts where you need to jump to can be very far in memory, and you need to maybe fetch it from memory, and it's not in the cache, so you don't get it. So what is good? Yeah.
When we write code, should we just assume that the branch predictor will predict that the branch is true by default?
I think it's maybe Anders knows this more, but I think it will choose not taken first.
I think so too.
Yeah, so it choose the fall through path first.
But if we take one of the branch like a little, does it predict the next time that we take it again?
Yeah.
Like how intelligent is it? Does it only remember the last branch that was taken, or does it remember?
Okay. This I think we can have another hour talk about it. Yeah. Maybe for next time, but it doesn't. Most intelligent branch predictors that nowadays in computer, they use the history and also from where you come, in which path, etc. So but that may be an interesting talk for next. But I don't have time to go into that. I think, yeah. But in either case, it will try to predict as best as possible, and it will normally think not taken just because of this reason is that fetching is easier when it's not taken branch because it's closer into memory. Yeah.
Not only the branch predictor, it's in the cache. So if you already fetch the hot path, maybe the rest of the hot path is in the same cache and in the instruction.
Yeah, exactly. So this is a good step up to my next slide. So untaken branches are easier. Actually, I don't know whether it's always true now anymore. I think they can, but you could say you can take 2 branches if they are well aligned. In memory, you can take 2 untaken branches in 1 cycle, but a taken branch takes 2 cycles often. So that's a big difference. So you lose 2 cycles. Yeah. So these slots 2 times there will be a stall. Yeah, of the front end bounds. Yeah. So and why is this better? Is because the front end kind of fetches memory in chunks, 32 bytes chunks. Before it was 16 bytes, but now it was 32 bytes. So whatever comes after the jump, and you actually take the branch taken, then that's instructions or memory that you wouldn't have need to be taken. And that's all then polluting the cache and maybe evicting some things that you were using very much. So you would like to avoid that as much as possible to have cold code in your cache. You actually want to have only hot code in your cache if you want to. Yeah. Okay. So other things you can do, I think you have systems that also try to do function splitting so that they have
more variability or more decisions that they can make to put this hot code together with the other hot code. Yeah. To give an example, a good example is something that's called Google Propeller, and they can do this for you. So they analyze, I think it's a post-link time optimization. So they get your binaries, and they have profiled Clang. They took some of the perf profiles, used that data to make a more propelled Clang. Let's just say that. So they improved this hot code layout. So again, yeah, I keep doing this mistake again. But okay. And what you see here is that only doing that, or only, yeah, it's a lot of movement, you get 4% less walk log time compared to the baseline of Clang, which were also already optimized with profile guided optimization and LTO, for example. So, and 4% is a lot. If you do this, I don't know who said it on the first day, 1%, 2%, you can just remove. Yeah, you don't need to use so many computer servers anymore. It's a huge deal. 4% seems small, but it's a huge deal if you look at it in the big picture of a data center, which they have this loop, feedback loop, compiling, profiling, compiling again, or linking, improving. So if you can do this much faster also, that would be good. Okay. Now you see also, this is a picture from the paper that I had published about it. So on the left side, here they used profile guided optimization and link time optimization. So it was already an improved version. They want to see how much better it was. And I think they had 7% improvement, but that was with an older servers, etc., older CPUs. So probably we had here some improvements now when I tested it on the front end side of the hardware I used. And you see on the x-axis is time, and on the y-axis you have basically an idea on the location where memory is accessed. So this is the offset of a certain memory address. We just didn't want to write, I think, all the memory addresses long, because then the picture would be a bit confusing. But if you see on the baseline, you see that the accesses are much more spread over time, temporally and spatially. And that's why it's not so optimized. But if you see on the propelled version, you see a band, much thicker band, much less spreading out of accesses. So this is not really lines, it's like access points. Yeah? It's like at that time I need to access this memory part at that time. So it's small little points that form a line. So that means here that in time you're basically accessing very close memory, very close to each other over time. And in the bigger picture also, compared to this one. So that means much more of your hot path will be in the cache. You won't have so many page walks that you need to do. So I think this picture shows well why you get this improvement of 4%. Okay, questions? Yeah?
Below the purple band on the right, there is a white band. So you also access memory that's very close, less.
Here you mean?
I don't know how far that goes.
Yeah.
So it's a trade-off that you have to look consistently a bit further, but...
Okay, no, this is... okay, I have this. These are basically memory locations. Absolute memory locations, or virtual memory addresses. So it doesn't matter so much the offset. We could have had the band here. That would have been fine, as long as it's close to each other. So you see it as a map. Yeah, a lin.
So it's not offset from previous instruction.
No. Yeah, the absolute offset. The absolute memory address. Sorry for the confusion. I think that's correct. It's good that you ask. Yeah. Yeah. Next one. I think I have 10 minutes. Yeah. Yes. Okay. Then maybe the next one. So bad speculation part. So that was another type of slots. In this case, bad speculation, branch control, control speculation, binary search. I saw the talk of Andre, so this will be disappearing into nothing. Yeah. So this is typically a search of the lower bound. And why is this bad speculation? Why do we get bad speculation here? I would like to have shown the numbers, which I had before, the same graphs, but then bad speculation, but I actually couldn't reproduce it on the computer I had. So it differs also per hardware that you use. But let's suppose this is bad speculation in the bigger picture, and this comes because of this comparison. This is a comparison that can go either way, about 50% left, 50% right, so it's very difficult for the predictor. On top of that, you have a memory access here, and if this is a very big arrays, it won't be in the cache, or not in the closest cache, maybe in L2, or maybe into memory. So in the meantime, while you're waiting for this memory address to be for this value to get from the memory address, you're speculating. And you can do that about 45 branches deep, which is quite a lot. So you will discover it very late. So you get a lot of bad speculation if this is wrong 50% of the time. So that's the reason why this will be worse when it comes to speculation. I have here a picture of a certain area size. I got this example from actually a very good book, I thought. It gives you also insights into hardware CPU. It's online available. It's from Sergei Slotin. It's called Algorithmika, if you're interested. Very good to read. They have a Russian version, but it was difficult to read for me. And they have an English version that is up to date, but the Russian version is a bit, I assume more up to date. That's what it tells me in English. That's what it tells in English. So what they did then was write another version of this binary search, a version that basically doesn't allow you to speculate, because here, this if statement now, this if statement will be transferred to what they call a conditional move. So you will only put the x value there when this condition is true. Okay? So you don't have this branch speculation here. It will end up in an ordinary instruction. It's called conditional move. So you won't be having this comparison jump instructions that we have seen before. So there's no ending of the basic block, so it doesn't need to predict anything. So that's why we don't get a bad speculation thing here. So what you see here, this is basically branchless programming, right? Yeah. So you try to avoid the branches, the jumps in your code. So here you see that the branchless version is much better for a certain that the Norwegian words there also, for a certain, how large the area size is. But from this point, it starts to be worse. Any idea why this can be? Why this gets now more back-end bound? Why do we need to wait? Because we removed all the bad speculation. Yeah, exactly, yeah. So you will, so you remember this tree, normally it will traverse and it will try to do the loads what it can, etc. And so it would already prepare, to some extent, not perfectly, your data so that it put in the cache. Okay, not perfect because it doesn't know exactly what to do with the 50% case, but it will do it rather well. Yeah. But we can improve it. We can improve this memory boundness, so waiting for memory, because we don't do the loads anymore, as we would do with the speculation mechanism. So we can do this by changing the layout It's something called a very good paper from, I hope I pronounce it well, from Eitzinger. It's kind of Eitzinger layout, where you're going to lay out the array according to how you access, how frequent you access the order, how you access actually your binary search. So let's say you have an array from 0 to 9 in this case. You would first access this one, then you would try to access 3 and 7, then you would try to access 1, 5, 8, or 9. If you go, if you have your binary search in your head, and 0 to 4. Could have been balanced, I would have even have a better picture, but you could rearrange your array from 0 to 9 to this way and in this way, and then when you would prefetch now, you would know if you're here, you would maybe prefetch this in memory, 3 and 7 already, so you're much more likely to get your data into the cache because it's ordered according to you have accessed. So it's more temporal localities. You would have more elements that are correct in the cache. So this is how it would access. So you start here, 15, then you go here, and then you jump to here, and they're all these parts. They're all close to each other. What you need to. So here you can see the frequency graph again. So by changing this layout, you can get a much more improvement. And by prefetching it, you can get much more an improvement over the baseline one, the baseline lower bound. Also for the bigger area. So look at the yellow here. That's it for me. I think that's, I hope you see that a modern CPU does a lot to increase performance. I think performance tuning while understanding the underlying CPU is important. Otherwise, it's very vague and it's difficult to know what to do. So that's why I like the top-down approach. Every CPU is different, which I found out myself. So measure also on different hardware. And I also showed that if you think quite creatively, you can, with some micro benchmark, understand the less well-known CPU features. So that was it for me. Thanks a lot. Yeah? Yes? Okay, shoot.
Does it any harm to slap unlikely into on any place where I think it's probably unlikely?
I think I think it's if you slap it everywhere where you want to, then it's likely that it won't get the best result, because what do you do if you have unlikely on different paths, or what would the compiler know? Or you put likely and unlikely on the same path, so then it gets confused. So so I would use it sparingly, once you detected where the problem is.
My question is, without actually measuring as a, let's say, best practice, just put it in places and does it harm, or is it pretty much your
I would first measure and see where it is, where you put your effort also. So the.
My other question is, does all this describe also relate to ARM?
Yeah, I think more or less. Yeah. So of course, many details are different. Yeah, they have a different way. I think, and also ARM has probably also an in-order processor. Like so it's difficult to say ARM. Yeah. So yeah. Other question? Was that it? Okay. Thanks a lot. Yeah. See you after.